Okay, so last time we talked about a continuous function, okay? How to define a continuous function. We say, okay, if a sequence in its domain converted to another point, then the f values of that sequence will form a new sequence, right? F of xn, which is a new sequence. This new sequence will convert to a number, which is f of x0, right? So then we call it, it's a continuous function. Okay, so now let's look at the which is called extreme value theorem. This theorem you should be very familiar with that because you have used this theorem in the calculus, right? Calculus 1 course. So the extreme value theorem, roughly speaking, just the continuous function on a closed interval, then it must have the maximum and the minimum values, right? So this is the extreme value theorem. But here, today we will revisit this theorem, okay? And we want to prove, okay? Prove the theorem. And this is the one of the most important theorem in the calculus. So before that, let me introduce some notations. Okay, so here is so we let f be a function from D to R. Okay, so that what does this mean? This means the D is called the domain. Okay, D here is the domain. The domain means the collection of the numbers we can plug into the function f. Okay, and R is, that means that after function f, okay, f of x would be a real number. Okay, will be a real number. So another important definition, which is called the image, okay, or the domain, or the range. The image or the range of the function f is this one, is collection of the numbers y, where y is what? Y equals f of x, and for any x in the domain D, for all x in the domain D. Okay, so your x runs through the whole domain. Then you have the corresponding f values. Okay, f values. So the collection of these f values is called the range or the image. Okay, so we denote the set by this symbol. I use the 3, this one. The symbol means it's defined by, we use this symbol, f of D. D is a domain, okay? D is a domain, f of D. D is the domain of f. So f will map its domain into its image or its range, okay? So f of D is defined by the range of this function f, or the image of this function f. Okay, so now let's look at what is the maximum value. So we say a function f attains a maximum value on the domain D if there exists some number m which is in its range or its image such that y is less than or equal to this m for all y in its range. Okay, f of d. So then we call it's the maximum value. So all the images will be less than or equal to this capital M. And this capital M is in its domain or in its range, okay? The capital M should be in its range or in its image. Then we say this M is called the maximum value. Similarly, okay, then this M is called the the maximum value. Maximum value. Any number x in D such that f of x is equal to this m. So where we can obtain this maximum value, we obtain as the some numbers x in the domain, right? Such that f of x equals m. This x is called, this kind of x are called a maximizer. Are called maximizer, okay? This is the maximizer. Maximizer means the x values. Maximum means the f values, function value. Okay. So this is the definition for the maximum value and the maximizer. So the next definition is the minimum value. So we say a function f attains its minimum values on the domain D if there exists some lowercase m in its range or in its image f of D such that y is always greater than or equal to this lowercase m for all y in its image. Okay, and this m is called the minimum value. Any x, any number x in its domain D such that f of x is equal to this lowercase m. This kind of x is called minimizer. Okay, minimum values means the f values. Minimizer means the x values, the domain. Okay, in its domain. So here is some examples. Okay, so this is the minimizer and the minimum value. So now let's look at some examples. So we have a function f, x, f, which is maps. The domain is open interval from 0 to 1 to a real number. Okay, by this one, f of x equals 2x. Okay, f of x equals 2x. The domain is an open interval from 0 to 1. Okay, so we can claim that this f has no maximum values. Has no maximum value. Why? Since for any x0 in the domain 0, 1, because f is equal to 2x, 2x is increasing function. So f always takes a large values on the interval from x0 to 1, right? For any number x0, you can always find some values between x0 and 1, such that this f value is greater than this f of x0. Since arbitrary, right? x0 is arbitrary, so there is no maximum. You cannot obtain the maximum values, right? Similarly, but okay, here some student may ask, okay, what about 2? 2 is not called the maximum value. 2 here, when x equals 1, right? F equals 2, but 1 is not there, right? But 2 is called the supremum of the function f on the interval from 0, 1. Okay, 2 is the supremum. But 2 is not in the range in the image of f from 0, 1. Right? 2 is the supremum, but it's not a maximum. So you can see the difference between the supremum and the maximum. Okay? If a function has a maximum, then this maximum is the supremum. But if a function has a supremum, the supremum may not be the maximum. Okay, because the supremum is kind of limit, right? It's kind of tendency. It will not be, it may not be in its domain, in its range. Okay. So similarly, you can see, okay, this one. Similarly, f has no minimum also values on the interval from 0, 1. But we know 0 should be the infimum of this f, right? 0 is the infimum. 0 is equal to the infimum of f. Infimum of f on the interval from 0, 1. Okay, but it's not. But 0 is not in the image of f on the interval from 0 to 1. Okay. So this is the one example. So may not be, this is a continuous function, no problem, right? But this continuous function may not have the maximum and minimum values. Okay. And here, the one thing is this domain is an open interval. Another example. The same thing, a similar one, okay? F is also from 0, 1 to the real number by f of x equals 1 over x, right? And this f has no maximum or the minimum values, right? On the interval from 0 to 2. This f has no minimum or maximum on the interval from 0, 1. We can use the graph to help you to understand. This is 0, 1, right? 1 is here. So the graph will look like this way. You can go up forever. Okay. Why? Okay. The reason is, look at the image. The set of image is a set of the y values, right? F values. This set is not bounded above. Right? From the graph, it will go up forever. Right? It will go up forever, so it will not bounded above. Right? since f of 1 over n is equal to n, right? F equals, when n is increasing, the f values will blow out, right? Blow out to infinity. So this has no bound above, no upper bound, right? But it's bounded below by 1, right? This is 1. This is also 1. It's bounded below by 1. The f values is bounded below. But this one is bounded below by 1. However, this one is not, but this one is not in its range, in its image, right? Actually, this one is equal to the infimum of this f on the interval from 0, 1. Right. This is the infimum. So this is another example, a continuous function on open interval. It may not have the maximum or the minimum values. So on what kind of condition the continuous function must have maximum and minimum values, okay? So before that, that is the extreme value theorem. Before that, we want to show another lemma, which will be used for the proof in the extreme value theorem. This is the lemma 3.10. Okay, so we let function f, which is from a closed interval from a to b to r. Okay, so that means the domain is a closed interval. This one be this f be a continuous function. Continuous function. Okay, then the image of f which is what? Which is f of from a to b, right? This image is bounded above. It's bounded above. Okay, if a function is on the closed interval, the domain is closed interval, then its image would be bounded above, have an upper bound at least, right? So in other words, i.e., there exists some constant m, okay, such that f of x is always less than equal to this capital M for all x in AB. Okay, so this is called the bounded above, right? We can always find the upper bound. If x runs through the whole interval, then f values are always less than this, less than equal to this capital M. So now we want to prove that. Okay, the proof is okay. So here the proof, the idea of the proof is we want to use the contradiction. Okay, suppose we have no this kind of number, right? We have no upper bound. It's not bounded above. And we also want to use the sequential compactness theorem. The sequential compactness theorem says, okay, any sequence on a closed interval AB, then this sequence must have a convergent subsequence. And the limit of the sequence must be inside this closed interval AB. So this is the compactness sequential theorem. Okay, a sequential compactness theorem. So we will use these two. Let's prove it. So we assume there is no such number m. Okay, so we cannot, for any number, we can always have some f of x which is greater than this number. Okay, for any number m, you can always find. In other words, for any number, for any m, there exists some x in AB such that f of x is always greater than this, equal to m, greater than m. So this is called the, it's not bounded above. Okay. So we assume there's no such m. So that means we assume the set is, the image is not bounded above. So what does this mean? That means for any number m, you can always find some x in the interval in its domain such that f of x would be greater than this m, no matter how large the m is, for any m. Okay, so now using this information, let's define a sequence. Okay, xn in AB such that f of xn is greater than or equal to n. We can always do that, right? Why? For example, if we take m, this m is arbitrary, right? Let's take m equals 1. So it says, okay, it must sum x values such that f of x would be greater than or equal to 1, greater than 1, right? We denote that x value would be x1. If m equals 2, then we have another x such that f of x equals greater than 2. We denote that x to be x2. And m equals 3. You have another one, all right? Greater than 3, f of x greater than 3. We denote that number x to be x3, and so on. Continue. When m equals n, this n, okay? Then we can always find some x values such that f of x is greater than this n. We denote that number to be xn. Continue this way, then you can form an you can form a sequence, right? x1, x2, x3. x1, f of x1 greater than 1, f of x2 greater than 2, f of x3 greater than 3, right? You can always define this one. We can do that, right? Okay, then we can use the sequential compactness theorem. By the sequential compactness theorem, there exists, okay, it says, what's the sequential compactness theorem? Let's check. This helps you to remind. Okay, so we talked the last time. Oh, not last time. It should be in the chapter 2, right? Should be in the chapter 2. Yes, this is sequential compact. It says, okay, sequential compact. The closed interval is sequential compact. What does this mean? This means what? Let's look at the sequential compact. What does it? There for every every sequence in this set, sequential compact set S. This every sequence must have a convergent subsequence, and the limit of this subsequence must be inside. Okay, so this is called the sequential compact. And this theorem tells you that the closed interval is a sequential compact. So that means for every sequence in this closed interval, you can find a convergent subsequence. And the limit of that convergent subsequence will be inside this AB. Okay, will be in this interval. Okay. Let's go to our proof. Okay. So now we have a sequence xn in the closed interval AB. And we know closed interval AB is sequential compact, right? So that means the compactness theorem. It says sequential compactness says this closed interval AB is a sequential compact. Okay. So in other words, there exists a subsequence of the sequence of this sequence. Okay, a subsequence which is x and k. Okay, k is the subscript of n, not n times k. Okay, n sub k. So we must have a subsequence that converges to x0, where this x0 must be inside this closed interval. Okay. Okay. So we have another condition. It says this function is continuous. We never use this condition, right? So here we want to use this condition. So since with this subsequence is converged to x0, x0 is inside AB, then since f is continuous on AB, then what does this mean? A function, if you have a convergent sequence, f is also continuous. So f of this x sub n sub k will converge to f of x0. Right? But then we have the contradiction. Okay. We say that f of xn is greater than n. So it's unbounded, right? Then you say, okay, it's unbounded, but the f values of this subsequence is convergent. It's not bounded. It's bounded, right? So this is the contradiction. Convergent must be bounded, right? If we have a convergent sequence, it must be bounded, right? So then, so it is contradicts. It contradicts. Contradicts the fact that fact that f of x sub n sub k is greater than this n sub k, right? Because xn is greater than f of xn greater than n. So now we take n to be n sub k, right? And this one, we know this one is always greater than k, right? Greater than equal to k. This is for all k, which is a natural number. Right? So it says unbounded, right? Unbounded. However, it tells you it's bounded because it's convergent. We know we have the theorem says a sequence is convergent. This sequence, right? This sequence is convergent. Then this sequence must be bounded, right? Do you remember that theorem? A sequence is convergent. It must be bounded. Bounded may not be convergent, but convergent must be bounded, right? So this is the contradiction. So here is unbounded, but you say, okay, it's bounded. So this is the contradiction, right? Okay. So f of AB, this is the image, is bounded above. Is bounded above. Okay. So now we will use this lemma to prove our extreme value theorem. So this is the end of the proof. So now let's look at the theorem 3.9, which is called extreme value theorem. The statement is quite easy, right? We say a function, a continuous function, f, which is from a closed interval AB to R. This function must attain both a minimum value and a maximum value. Maximum value, sorry. Okay, so this is the extreme value theorem. It says, okay, you have a continuous function. The domain is a closed interval. Then it must have both minimum value and maximum value. Okay. Now let's prove it. Let's prove it must have the maximum value. Okay. It must have the maximum value. So now, first thing we need to do is let's denote some symbols. S be the set of the function, the image of this function f. Okay, remember, keep in mind this S is the range. Okay, so by the lemma, we just prove. By the lemma above. This S is bounded above, right? Is bounded above. So the idea is we want to show that. So since it's bounded above, we want to show that this range must have the superman. This is one thing. And this superman must be inside. If the superman is inside this range in S, okay, the superman of S is inside S. So that means that superman must be the maximum value, right? Okay, so this is the idea. So the first thing is if this one superman exists or not. Do you remember we have which is called a completeness axiom? We studied in the first chapter. Completeness axiom. What's the meaning for the completeness axiom? So if you have a set of real numbers, okay, this S must be real number set of real numbers, right? No problem, because F is from A, B to R. R is a real number, right? Real number set. So the image must be real numbers. So if you have a set of real numbers, and this set is bounded above, then the superman must exist, right? Do you remember that? This is called a completeness axiom. And we also have a theorem we proved. I'm not sure. It's a homework or not? Oh, no, it should not be a homework, right? Anyway, we have proved another theorem which said, okay, another result that we use the completeness axiom says, okay, if you have a set of real numbers, this set is bounded below, then the infimum also exists, right? Do you remember that? We have these two results. Okay, so now we just use the completeness axiom. Okay, the completeness axiom says, okay, so this S is a set of real numbers and which is bounded above. So then the superman of S exists. Okay, the superman exists. So now let's let C to be our superman. C is equal to the superman of this S. Okay, the superman of S. So the next thing we want to show that there exists. We want to show that the C is also in S. So that means, so we want to show that there exists some X0 inside this AB such that F of X0 is equal to the C. If we can show that, then this superman, this C must be the maximum, right? Okay. So now let's construct a sequence. Let's construct a sequence Xn in AB such that F of Xn is less than C. This is no problem, right? Less than C. C is the superman. Of course, less than C, right? But it's greater than C minus 1 over N. We can always have that. The reason is still the same reason. It's the superman. What's the meaning for the superman? Superman means the least upper bound, right? If you subtract a little number, it will not be an upper bound anymore. So that means you must have some Xn, which is greater than this number, right? For example, if you take N equals 1, F of X, okay, C minus 1, 1 over 1 is 1, right? C minus 1 is not an upper bound because C is an upper bound. So you must have some X inside AB such that F of X is greater than the C minus 1. We denote that X to be X1. The same thing, N equals 2. C minus 1/2 would not be an upper bound anymore, right? So you must have another X, which is F of X is greater than the C minus 1/2. we denote that x to be x2. Now you continue this way, x3, x4, and xn, right? Then you form a sequence, and this sequence is greater than c minus 1 over n, right? But less than c. Less than c, no problem, because it's a superman, right? Okay. So we just use this sentence to describe how do we construct the sequence. The sequence must exist, right? This sequence, just as I said, how to construct it? We take n equals 1, c minus 1. We must have a value f of that value is greater than c minus 1. So we take that value to be x1, right? x2 and x3 and x4 and so on. So this sequence must exist. Since c minus 1 over n is not an upper bound. The reason is upper bound. The reason is C is the superman, is the least upper bound, right? Okay. So now let's continue. So we have a sequence. Again, we have the same situation as we proved in our lemma. We have a sequence in a closed interval. And this sequence, okay, so our idea is we have a sequence in this interval. This sequence satisfies this inequalities. Okay. Then we have, since this interval is sequential compact, so that means you must have a convergent subsequence of this sequence. Okay. And the limit, we want to show that that limit is the x0 here. Is the thing we are looking for. F of x0 should be equal to c. Okay. So by the sequential compactness theorem, there exists a subsequence which is xn sub k in the original sequence xn, such that xn sub k, this sequence will converge to x0 when k approaches infinity. And this x0 is inside AB. This is the compact sequential compactness. Right? So since F is continuous, US and UOUS, okay. Continuous on AB. Then since you have this sequence, okay, a convergent sequence, so by definition of the continuity, it says f of xn sub k is convergent to f of x0. Okay. On the other hand, we note that f of x and k, and x and k is a subsequence, is a member of xn, right? So it must also satisfy this inequalities. We just replace n with nk. If k approaches infinity, nk would approach infinity, right? So here is one thing we want to use, which is called a sequential, which is a squeeze theorem you have learned in the calculus. If both sides approach the same number, then the middle one will also approach that number, right? So the limit k, sorry, k approaches infinity of f of x and so k would be equal to c. And we know f of xn will approach to x, f of x 0. Then f of x0 must be equal to c. Right? We only have one limit. Therefore, c is inside this S. So the superman is the maximum, right? So C, which is the superman of S, is the maximum value. Okay, so we proved one part. We need to prove another part, right? But the other part, we can just use this part. How do we use that? The idea is the following. To see that, and it also has a minimizer. It has a minimizer, okay? A minimum values or minimizer, doesn't matter. Minimum value. We can prove that by letting G is equal to negative F, which is also from A to B. And we notice that the maximum of G is the minimum of F because it's equal to negative, right? So we just let G is equal to negative F. So G is still from the interval from A, closed interval from A to B, right? And it's continuous function because negative F is still continuous. And we just prove that if you have a continuous function on a closed interval, it must have the maximum value, right? So G must have the maximum value. G has the maximum, but the maximum value of the G is the minimum value of F because G equal to negative F. So this is the way we prove, okay? So we will not repeat it anymore because we just need to use the same way to prove this, the function, the maximum value of G exists, okay? So this is the extreme value theorem. Okay. So the next part, I want to show you something, some result we used in our proof. That is this one, squeeze lemma. If both sides approach to the same number, then the middle one approaches that number also. This is the thing we needed to prove, okay? Because I didn't give you that result, but we used here. Okay, so this is the one thing. But you know that result, squeeze lemma, in your calculus, right? Another one is the maximum of G is the minimum of F. If G is equal to negative F, we still don't have this result, right? But we can imagine, of course, it's true, right? But I can show you the proof for this result. to confirm yourself, okay, we can use that. Squeeze them. Okay, so this lemma is not given in your textbook, but I can show that. So we let 3 sequences, AN, BN, and CN, be sequences. If AN is less than equal to BN is less than equal to CN, for N greater than equal to some capital N, which is a natural number. And the limit N approaches infinity of AN is equal to the limit N approaches infinity of CN is equal to L. Then the sequence BN converges to L. Okay. So why I want to show you this result? The reason is it's a good practice to use actual and language. Okay. So when we prove some sequence converge to some number, one main rule is the actual and language criterion. Okay. Let's prove it. I'll give you time to write down the result, the squeeze lemma. Okay, so now let's prove it. The proof is not hard, very straightforward, but we just use the actual language to describe the limit again and again. Okay. So now let's look at any epsilon greater than 0. For any epsilon greater than 0, since AN has the limit L, what does this mean? This means then there exists a capital N1, right? Such that AN minus L is less than epsilon, right? So this is the definition of the limit of a sequence, right? What does this mean? This means AN is less than epsilon plus L less than L minus epsilon. Right? We just rewrite this inequality without the absolute value sign for N greater than equal to this capital N1. So this is the definition for the limit AN approaches L. The same reason CN, since CN approaches L also. So that means then there exists a capital N2, right? We cannot use the same capital N, right? We don't know because they are the different sequence such that CN minus L is less than epsilon. All right, what does this mean? This means Cn is greater than L minus epsilon, less than L plus epsilon. For N is greater than equal to this capital N2. Okay. So the next idea is we want to show that Bn is also between L minus epsilon and L plus epsilon when N is large enough, greater than some constant N, right? So in other words, we need, use another color, we need this inequality to be true. This inequality to be true. and this inequality to be true at the same time, simultaneously. But for each inequality, the index n for this inequality should be greater than this capital N, right? So this inequality, this n should be greater than or equal to this n1. This n should be greater than or equal to n2. What we should do to make these three inequalities to be true at the same time? Any idea? We use this technique already. Let what? Let n tilde to be the maximum value of n1, n2, and n, right? If lowercase n is greater than this capital N tilde, so that means this lowercase n must be greater than or equal to n2, must be greater than n1, must be greater than n. So these three inequalities to be true at the simultaneous, right? This is the technique we often use, right? We use a lot in our proof. So we have an less than or equal to bn less than or equal to cn, and the cn is less than L plus epsilon. An is greater than L minus epsilon, right? So we combine these three inequalities together, you will have this inequality. This is true for n is greater than or equal to this n tilde. Now let's look at, just highlight the thing we are interested in. L minus epsilon is less than bn less than L plus epsilon. What does this mean? So b minus L is less than epsilon for n is greater than or equal to this n tilde. That is the definition that the limit n approaches infinity of bn is equal to L. Right? So now let's rewrite. Let's look at this result again. Okay, I use another. Let's look at the proof again. For any epsilon greater than 0, there exists a capital N tilde, right? Which is formed by this way, because n1, n2, and n exist, and we know that number, right? Such that b minus L is less than epsilon for n is greater than n tilde. That is the exact definition, right, for the limit of a sequence. Okay, so we finished the proof for this part. Is it hard? No, not at all, right? What I did nothing. I just restate. I just used the epsilon language to restate this limit, the sequence, the limit of the sequence, right? I just restate the limit of the sequence, right? The only technique we use, which I just take a common n, right? I believe many students think about it. You must can find this one, okay? The idea is we want to make these three inequalities to be true at the same time, then you can combine them, right? So it's just take your, maybe it's just if you are not familiar, maybe you can think about 30 minutes, then you may have that. Okay, it should not be hard because we have seen this kind of technique already. So you have some ideas should behind, okay? When you think about, then this idea will pop up, okay? So when you do the proof, don't too worry about the proof. You need to write down somewhere. Okay, so what's the limit? The limit means this one. Okay, because if you have the limit, we can do nothing, right? We should use some precise description, right, to describe this one, we use some language, math language to describe this notation, right? The notation has nothing to, it's useless, right? Notation is useless, but the math language is useful, okay? Yeah, you may not write this proof perfectly at the beginning, but you can on your scratch paper, what's the A and approach the L? Okay, it's equal, it's the meaning is this one. Okay, what is C and approach the L? It's the meaning is this one. Okay, what we want this one. Okay, you may think about, okay, we look back to our condition. Okay, it looks that we have all the inequalities. Then you can think about how to combine them. Okay. Okay, so this is this result. So another fact we use a lot in our class, which is this one. I use just its lemma. Okay. So next time we can use out without any. You don't need to worry about your result is correct or not. Okay. You should be very confident to use this kind of result because we have proved. So we say the function f, negative f, attains a maximum value on the domain D if and only if this function f, which is from D to R, okay, attains a minimum value. Okay. When attain the maximum value, then the opposite function, negative f, would be minimum value, right? Negative of negative would be f. Okay. So since this is the if and only if problem, so we need a tool with two directions. Okay. So in your home, when you see if and only if, you should give me the proof for two directions. Okay. No matter how easy it is. Maybe you one direction, just one sentence. That's okay, but you should still give me the clear proof. Okay. So don't just write some confusing words and ask me to guess what you are thinking. Okay. So this is the idea. So this is the things where I have some students have some troubles in the proof in your homework problem. So they just write down some confusing words, a lot of words, and ask me to guess, okay, if they are right or not. So now let's look at this direction. We need to have two directions, okay? So suppose negative f attains a maximum value. So this proof should not be hard. What does this mean? Okay, the first thing, what does this mean? It's just maximum value. Okay, we should need to use some math language, right, to describe it. What's the meaning for the maximum value? So that means there exists x0 in its domain D such that negative f of this x0, this one is the maximum value, is greater than or equal to negative f of x, right, for all x in D, for all x in D. Okay. So in other words, from this definition, from this inequality, we multiply -1 on both sides. So f of x0 is less than or equal to f of x for all x in D. Okay, what does this mean? F of x0 is less than or equal to f of x for all x in D. So f of x is f of x of fx0 is the minimal in D. Oh, sorry. It's just the minimum values, right? It's the minimum value of f. Right? Because this is the definition, right? What's the minimum? This is to give you the definition of the minimum value. All x f values should be greater than or equal to f of x0. All right. So this one is the minimum because x0 is inside. X0 is in the domain. So f of x0 also should be in its range, right? For this direction. All right. The other direction is the same. Just repeat it. Okay. Suppose f attains a minimum value. Then we want to show that negative f will attain the maximum at the same point. Right? In other words, so there exists x0 in the domain D such that f of x is greater than or equal to f of x0 for any x in its domain. In other words, let's multiply -1 on both sides. Negative f of x would be less than or equal to negative f of x0 for all x in the domain D. So negative f attains negative f of x0 is the maximum value of what? Of this function, a negative f, of negative f. Okay, so we prove. For this proof, nothing special. Why? I didn't use any technique. I just restate what is the maximum value. The maximum value means this one. The only technique is which I just multiply -1 on both sides. Because our aim is f, right? Here. In the first part, our aim is f. So we multiply here negative f. So we multiply -1 on both sides. This is a very natural thinking, right? So we multiply -1 on both sides, and you have, okay, when you look at, okay, this one is the minimum value. All right? x0 at x0, negative f would be the maximum, and x0 f would be the minimum. The same thing for this one. Right? The same, exact same, almost the exact same. Because here is we start from f, but we need a negative f, so we just multiply -1 on both sides. Right? Nothing special, right? I just restate, use the math language to restate the maximum values and the minimum, just using math language to restate the definition we already know. Okay? So for the proof, one thing is very important thing is the definition. The definition is really important in the proof. Okay? Which you cannot just say, okay, it's maximum value, maximum, minimum value. It's useless, right? If you just say maximum and minimum value, what does this mean? You need to use math language to describe it. Okay. So this is the proof for this part. Okay, so any questions? If you have no questions, yeah, we can stop here. So next time we will talk about the intermediate value theorem. This is another theorem you have learned in your calculus.